Hey everybody, Tom Jolene here. You all know who I am. We've got Braden from Price Industries, and if you've been following along with the blog posts. The first post was the most boring class ever, followed by some cheeky things about coils and fan coils along the way. But after having reviewed Braden's presentation last week and kind of going through the content. Now I'm coming up on my 30-year anniversary, and a lot of the information that I've found in here, I just didn't know. And it was my suspicion it would be that way. And my also suspicion is that you guys are going to learn quite a bit more than maybe you expected. So if you're working on a project and trying to pay attention to this, I'd suggest that maybe you just pay attention to this. And then also just a little preview for next year. We are working on our class curriculum being more of like a workshop. So instead of this lecture series, like we're going to lecture at you for a couple hours about coils and fan coils, next year we're going to be doing more workshop, as in, hey, here's a design challenge. While we're on this meeting, we're going to give you the tools to work. We'll give you a set of problems, and you guys are going to work through those, and then we're going to critique your answers and provide support. So that's something to look forward to. We haven't made the announcement yet, other than just what I announced right now. And so look forward to that. Without further ado, I'm going to turn it over to Braden, and of course, as usual, provide some color commentary where appropriate. So, Braden, take it away. Oh, and please give us a little intro on yourself too, if it's not one of your slides.
For sure. Yeah. No, thanks there, Tom, and thanks to everyone here for tuning in on this fine Tuesday. Definitely excited to talk about some of these different topics, and always love to see the different topics that are going around in the industry and the excellent events that Airflow puts on. But a little bit of intro myself. You might have seen this too, just as some of these email blasts were going out. But I've been at Price for 8 years now. I'm our project engineering manager on the air moving side. So focus on terminals, fan coils, blow coils, hydraulic valve packs, many different equipment of what you might see. But today is a little bit more of a focus on water coils and fan coils in a little bit. And for, I want to say, the last 5 or 6 weeks, I met with Tom there too. And we were kind of going over the ideas of the world of water coils, what all goes within these components. And when doing some research on this, I realized for myself, and what you probably even see for different engineers and contractors in the industry, that we simply take these coils for granted. And a brief other kind of overview of some things in my life there too, that I've realized when kind of going through this that I've taken for granted. One of them, I've recently got a new puppy that bites me all the time. I can appreciate dogs that I've owned before in the past that have not done that to me. Those things are like beggars for any of you pet owners out there. Also for any of you rec sports enthusiasts as well, any of those late night hockey games or sport games, how long it takes to recover after those. Definitely takes a long time in comparison to when I was around 20, 30 now. It starts to hit a little bit harder. And the last one there too, for any of you campers or backpackers out there, how good a home cooked meal tastes after eating trail mix for a week straight. But how does this really tie into water coils? Well, again, we take them for granted. For engineers out there, we see different formulas that are utilized to be able to expect performance of what we might see. Contracting side, we connect tubing to these water coils and just expect them to run at a certain flow that we might balance them to, and then just list them out in the schedule. We see these schedules, we see these different parameters, but when we kind of go behind the scenes of this, what different variables actually have an influence on this performance that we see within schedules? Does the coil itself have an influence on it based off of how it's constructed? And then also why I might be seeing some deviations in some of those formulas I might be using, versus what's actually being listed out within the schedule or from some of those different calculators we see there too. But with that, I'd say let's dive right into it in terms of our topic of discussion here. And why are coils taken for granted? Well, from a base level, seem like pretty simple equipment. Heavily utilized, I would say, within the industry as zone wire to air heat exchangers to provide thermal comfort for a space, whether it's going to be running heating or cooling to condition that occupied zone. Where you might see them standalone water coils, or where you might even see them too with retrofit equipment within the industry. But then also what we'll be talking about in a little bit here too, different fan-powered equipment or single-duct VAVs as well, whether it be sensible cooling coils, heating coils, or also handling those latent conditions there too. But when we actually focus and take a look at the coil itself, what we realize is there's a lot of different components and features that actually go into putting this coil together, whether it be its overall size, how many fins or what type of material is going to be used within the type of spacings, manifolds, headers, and then even the amount of rows or circuitry that's put into the coil itself there too. And what we'll learn here in a little bit is that each of these little things that are called out do have a play within, whether it be on the design side of what's capable from a manufacturer level, or also from a performance level of having an influence of what you're going to be seeing on your schedule or when you're connecting to this equipment within the field. So where I kind of like to first kick us off here too is taking a look at this performance more so from a user's perspective. So what does this look like typically on a day-to-day for determining this performance for these water coils? And then why we might even see some deviations even from, say, what's listed in a manufacturer's catalog. So one of the most common ways that we see calculating or initial step of calculating heat transfer for water coils is through this airside heat transfer equation. Simple, effective, to be able to determine how much MVH is going to be coming from a coil, essentially evaluating based off the temperature rise of the entering or those air conditions going through these coils at a certain CFM, how much capacity or BTUs is going to be coming from it. One thing that we'll really notice there though is at 1.085. which essentially is a constant. And not to give PTSD of going back to the university days there, but with constants has a high level of different assumptions that really go into play for making these formulas easier and simple to use. And the reality of that is that not all these assumptions are actually true of what you might see for that specific coil or the application that it's installed in, such as where it's positioned on sea level, how much of that coil is actually being utilized for that heat transfer that's going through it, and then even the overall profile of that air that's going to be passing through that coil there too.
That slide kind of makes me wonder about all the times that, if you had a coil that didn't perform and the engineer said, well, just give us a bigger coil and we'll transition in and out to it, and then assume that all the BTUs got transferred into that duct. Maybe they do, but it would be interesting to find out how much didn't.
Exactly. Yeah, and that's one thing that we even tie into there too. And similarly, what you're saying there, Tom, even for the water side of things there as well. Now, when we look at some of those fluid characteristics, similarly for a water side delta, that ideal condition that we might be targeting, especially when we're looking at what conditions are being fed back to your boilers within a given system, or chillers or heat pumps, key consideration for that parameter. But with that, again, also other forms of different assumptions that do come into play in terms of maybe even what insulation is going to be used, in terms of energy transfer for losses or gains of what is actually happening to that coil in the field, And then even for some of those older projects that you might see are retrofits or older systems, degradation of some of the surfaces of that coil, and what influence does that really have on its overall heat transfer there as well. And one kind of key formula I would say that a lot of people don't really take into account there too is the BTUs, or the capacity of the coil itself. The reality of this is that there are other different coefficients that do come into play when actually trying to evaluate the heat transfer at the coil level, such as the material level, which we're going to get into a little bit, of rows, spin density, and then also circuitry and utilized face area, but then also different coefficients that come into play based off of what material is used and then how that coil is going to be constructed. Can be a pretty complex formula, I would say, just as an initial viewpoint, but I would say for the manufacturing level, typically for these different softwares that you might use, whether it be Train Trace or a engineering toolkit, all of that manufacturer performance is built into those softwares just to be able to evaluate how much actual capacity has been measured from that manufacturer for that performance that that coil is going to provide. And how is that certified? To give us the peace of mind of what's being listed from that manufacturer, or that coil that they're making is what we can actually expect, but it's going to be in the field. Well, that's done through a Tri 410. So any of you that may have installed a water coil in the field or seen some of these products, commonly you're going to see this blue label that's going to be on that coil itself, essentially saying that this has been rated and certified to this AHRI program that essentially evaluates that published performance from that manufacturer or through that software is what you're going to be expecting. So it's a pretty stringent program in terms of how inline that capacity needs to be for that coil, and then also some of those different pressure drop characteristics. So your fluid side, as well as your air side pressure drop for those equipment there too.
Hey, Braden, just a quick question for you. And I don't know actually if you know the answer to this, which is always fun. So that's a new 2023 standard.
Mm-hmm.
I can't imagine coil testing has changed an awful lot. Was there?
To be honest, not much has been changed. I've sat in on some of these committee meetings there too, and to be honest, it's more so maybe adjusting some verbiage and section 8.1.7 or like certain sections within the standard itself. But in terms of evaluation, hasn't drastically changed. I think earlier 2000s, it did get more strict in terms of capacity level of what that acceptable tolerance would be. It used to be, I want to say 95 to now 97.5. Like there has been some of those adjustments over time, but reality, like there hasn't been too much of a change, I would say, for that.
Got it.
Mm-hmm. And where this also ties into a performance level is also the discussion of laminar versus turbulent flow. Important characteristic that will have an influence on that overall coil performance. And I guess maybe even just to open up to the chat just for some engagement here, which do you expect to be, whether it be laminar or turbulent flow, to have more predictable performance for a water coil? And right now, I think the chat function might not be working, so maybe even putting it into the Q&A function. See one answer there. Thank you, John, for putting that in the chat.
Thanks for sitting in today. Laminar is an answer. Any other answers? Oh, we've got another.
Perfect.
No, well, John Allen is dominating the Q&A function here, folks. So is anybody else got any?
Any other answers there too? Don't worry, this is not being evaluated there.
Wouldn't laminar be more consistent? That's our very own Logan Mumper.
Perfect. Thanks for your answer there too, Logan. Well, actually, and surprising there too, and this kind of ties back to heat transfer for those there too, and that haven't answered. The more predictable performance is actually going to be turbulent flow for being able to evaluate, because there really isn't much. I would say in terms of turbulent flow, it's going to be more of maybe it's disordered of what you would see of as that water is flowing through the coil. But in terms of predictability, that's actually where the most efficient heat transfer is actually occurring within the coil itself. So when you see and maybe write performance or generating performance through softwares, what we're actually going to see is minimums or maximums for those coils through those tools there too. And what those minimums typically are actually going to be based off of is that range in which it transfers, or it's predicted to transfer between turbulent and laminar flow. And what that actually equates to, normally it's listed as velocity, but I've converted it over to GPM, just as that's a little bit easier digestible to see, is that actually equates to 0.6 GPM per circuit for cooling and 0.3 GPM per circuit for heating. Commonly, if you're dealing with much more lower flow applications, a lot of the times you're going to see these softwares might give you a warning message or an error message. And the reason for that being is that they're trying to get you within that turbulent flow range, just because as we get below that, sure, we can extrapolate or interpolate some values for that, but it might not be exactly of what's actually happening at that coil, as it's much harder to evaluate for that laminar flow range. So now that we've looked at some of the different standards and performance equations that go into calculating expected results from a coil, let's actually take a look at what's inside a coil. And the first one being, and this is one that actually I don't have in my office right now, but do have one that chopped in half of a water coil just to be able to demonstrate it there. And the first one being fins. Aluminum fins or fins is going to be constructed in many different water coils that you would see in the industry. Essentially, this is where a lot of that heat transfer is going to be occurring from that air that's going to be passing through that coil as that fluid is passing back and forth through the coil itself. In terms of tubes that will, in terms of height of these components, typically these are going to be 1/2-inch tubes that are going to be passing through the coil itself. That actually has an influence in terms of what that overall fin height of that coil can be. Reason for that being is that we're wanting to make sure that based off of that overall tube height or what's being tube thicknesses that is being used in that coil, that the amount of passes that are going through that coil is always going to be leaving on the same side. There's a lot of coils that you see within the industry. We don't want the entry point to be on one side and the leaving point to be on the other. So a lot of the times with these coils, there's going to be restrictions on that overall fin height or how many different dimensions that you can do in terms of increments for a height of a coil, just because we're wanting to make sure that the entry point and the leaving point are going to be on the same side. Another common parameter that you would see when talking about fins and commonly see listed out in specification is going to be fin density. So how many of those fins are within an inch of space for that coil? Fin density is effective as it's going to be the thicker that fin density is going to allow for more transfer of energy or higher level of capacity. But one consideration for that being is that as we start to increase the amount of fins that are in succession on a coil itself, that also increases the amount of resistance that that coil is adding on our system, or when we're talking about fans, of how much energy that fan is needing to compensate for. So commonly, I would say for air moving applications of what I would see for terminals, fan coils, and blower coils, typically this is within that 10 to 14 fins per inch range. The reason for that being, as we discussed, if we were to get above that benchmark, we're going to see a lot of additional pressure that coil is going to be adding on our system or on that fan. And if we were to go below that threshold, let's say 8 or 6 or even below that, that's where it gets more exposed to having potential cracking that might happen at that coil or even as it's transported. Because this is not as, I would say, strong of material, especially as it's more spaced out. So you can only imagine trying to handle that within the field, a potential of maybe even damaging that coil as you're trying to install it into the ductwork of a system or as that product is being transported.
Just a quick question here, Braden. So if I was going to go through like terminal box and fan coil submittals for Price Industries, I can't recall that I've seen a 3/8 inch connection on any of those devices.
No.
Are there, if I have a 1/2 inch connection, is it possible that I'm transitioning down to a 3/8 inch coil, or is that?
Good question. So in terms of the coils itself, that's actually the tubes that are passing through it. Those connections, though, those are what are actually varying. Like these are not the end connections of the coil. It's more so the tubes that are actually passing through the fins.
You are dropping internally, there's a reducer at the coil connection, and you're actually running 3/8 inch tubes through some of these coils.
Right.
I did not know that.
Yeah. So yeah, definitely interesting. I would say in terms of where you might see some 3/8 coil, it might be for like some smaller coils, I would say within the industry there too, but more often not, especially for terminals and fan coils, the typical industry standard is 1/2 inch that are going to be passing through those fins.
Braden, looks like we've got a hand here from Joe Martini.
Oh, perfect there, Joe. You mind it looks like the chat function is now working for everyone on the call there too. So if you do have any questions throughout the presentation, feel free to drop them in the chat there too, and can kind of respond to those as they come up. Oh, no worries, Joe. An accident, that's quite all right.
No, Joe, you got to come up with a question now, so we'll give you a couple minutes.
Perfect. Next, we're going to pass on, and this is one that a lot of people are familiar with, but maybe not know how to determine, is rows. So I guess maybe even just kick off with another exercise for engagement. For this coil that we see on screen, can anyone tell me how many rows that we can expect for this coil? Bill kicking us off there too. Awesome. Jonathan, thanks for your response. Logan, again, thank you for your response there too. I'll give maybe 5 more seconds here. Julie, Kevin, thanks for your response there too. Loving the engagement now. Everyone's coming out now that the chat's up and running. That's awesome. A little bit harder to see just based off of maybe the ISO or ISO view of this, but this is actually a 2-row coil. And how do we determine that? Well, it's going to be the amount of vertical columns that is actually on the coil itself. Commonly, you might see this, especially with these helical flow or these tighter 1 or 2-row coils that we see in the industry, and maybe misinterpreting based off of just having one entry point, one leaving point dictating or saying it's a 1-row coil. But it's actually going to be the amount of columns that we'd see that are going through the coil itself. So in this case, this one being a 2-row coil.
You know what I like about that? I just, as a HVAC rep, and we've got like some folks from my team and then some really experienced engineers. You look at this thing and you go, well, everybody should know that. But without having been shown it before, we don't all know the answers. There were 1s, 2s, 3s, 4s, and 5s in the answers. So It makes me glad that we're doing this class, because I looked at it, I'm like, I think that's 2, but I'm not sure.
Yeah. And honestly, I think it's just something that's really just assumed in the industry, and you might not really get to see your eyes on a coil on a day-to-day basis. And I always think it's a really good example just to bring up there too.
Good.
In terms of what we're seeing in terms of trends of how many rows are utilized within the industry, we're starting to see higher amounts that are going to be required. What we're seeing for both terminals, fan coils applications for both heating and cooling conditions. And the reason for that being, we're seeing with chiller designs, these being at much higher elevated temperatures of what are going to be through that coil. And then with the utilization of high efficiency boilers or heat pumps, lower wire temperatures that are going through our heating side. And with that being for tighter restrictions in terms of either warmer cold water or colder hot water that's going through the coil, a little bit harder to achieve that same capacity of what we've seen for that coil. And we'll actually have a really good retrofit example to go over here in a little bit. But with that being, now we're seeing in a lot of applications having to increase the amount of rows that are being put on a lot of these equipments within the schedule. But with that, as we start to increase the overall rows that are on a coil, it's also adding that additional air pressure drop or resistance that that coil is going to be adding on our system, or that fan is trying to compensate for there too. So even for example here, another 1/4 inch of static that say a fan is trying to compensate for, in a lot of cases could be significant for trying to achieve the same results, especially when we're considering or looking at retrofit applications there too.
Yeah, there's one open question about an extension between, well, I don't know, an extension before the coil, and if it would hurt or help the heat transfer, which I think is implying like a extended casing kind of a construction, which I think the answer is if it's in a VAV box, it could, but it would be untested. So could you take a credit for it, I think is the answer. What do you think?
Yeah, no, I think that would be the case there too, of in terms of tested of with like an extension casing that you might be adding on there. I mean, there is the reality as we start to get really in the nitty-gritty, and I feel like that could be its own class in terms of influence of dampers on a VAV within a given system or other potential choke points. But with a lot of this performance that we'd see, especially when we tie it back to maybe even fan coils and blower coils, what we'll see is that these are actually under their own program there too of tested as a full assembly. So that adding additional length to it, it's really potentially not really going to make a difference because it's already been tested as a full equipment with both the fan and the coil in conjunction with each other there. A really good question there. And I started to dive into the weeds there too. I mentioned there earlier of evaluating the influence of increasing rows based off of the maximum, let's say, amount of capacity that can be achieved from a coil versus how much additional pressure drop that it's going to be adding on the coil itself there too. This graph here is just a comparison that as we increase rows of coil, how much of the maximum capacity of that coil are we achieving and how much additional air pressure drop are we achieving there too. And one interesting relationship that we see when evaluating increasing rows versus capacity and pressure drop is that there is the most or a more drastic increase between the first few rows of coil that is being added, and it's more of a linear relationship of how much additional air pressure drop or resistance that's adding on our casing. So a lot of the cases when working, let's say with single duct VAVs or lower rows of coils, the most significant increase on capacity that we're typically going to see is for those first few rows of coil that we're going to be adding on our system there. So something to even take into consideration that say maybe you initially have it spec'd out with a 1-row cooling coil for a product, and then now they're asking for maybe trying to achieve a certain capacity benchmark. Always even before just toggling or jumping to a 6-row or 8-row coil, more beneficial when even just looking at maybe that incremental step of some of the lower rows for adding to it there as well.
I think we all learn this exercise when we're just a little bit short on capacity. It's like, oh, just put a little more water through it and you get nothing. Like, wait a minute, I just doubled my flow and I got 15% more capacity. Like, why is this is the relationship
Yeah.
of diminishing returns.
I see a question here too from Jonathan. Was the most rows you've seen on a single coil? Well, from say a terminals and fan coil side of things, that'd be, I would say, 10 rows of coil. So 8 rows of cooling, 2 rows of heating, a typical one that we might see. I know it could potentially get much bigger too when we're talking about air handlers or like different equipment out there within industry, but I'd say that's the most typical maximum of what we'd see. So up to 8 rows for cooling, up to 4 rows for heating of what you might see there. The next example that I'd like to bring up, just because I thought rows was a really good one, is maybe even just quizzing everyone in the chat of how many circuits do we think that same coil, that same 2-row coil has on screen here. David had that one locked and loaded, single circuit. Thanks for your response. Sathan, thanks for your response there too. Give a little bit more time, Julie. Thanks for your response there.
It's too bad. We're going to have a little talk.
Yeah. Heidi, 6, awesome. Joe,
this is awesome.
Ben, thanks for your response. Lots of different responses there. And it's actually, for this coil, and I see a number of you had said it, is actually a 1-circuit coil, or essentially one fluid path in terms of where that fluid's entering into that coil and where it's going to be leaving from that coil. A lot of the times there, and I've seen a couple of you have said it there too, of maybe interpreting it as these fluid paths, of maybe just counting how many connections or entry points up are going into that coil. But what you'll actually see is that this is just one individual tube that is passing back and forth through that coil before the fluid is going to be leaving. So that's how it's going to be dictating that coil. And since I know all of you are now experts, let's take a look at a little bit of a bigger one. And this one's a grand finale of how many circuits do we think are on this 4-row coil. Jonathan, awesome. Thanks for your response there.
We've got an 8.
8.
We've got a 1.
1. Perfect. Well, maybe we'll kick off here too. These ones are definitely a lot more complex, maybe even tougher to read here too, just on the side. But it's actually very close with saying 8 is a 9-circuit coil, 409 circuit. So essentially, if we were to try to look at this overall header of where all these different fluid or entry points are going to be, very hard to see within this ISO view here there too. So kudos to those that even set 8 for this. But what you'll see is that can get very complex in terms of how many fluid paths that you might see circuit through the coil. And then you'll see that as you start to increase the overall rows of coil there too, the more complex are the arrangement in terms of what that distribution of fluid paths are as they go through the coil themselves.
And this became one of the things that I did want to share, because when you run Price's fan coil program and you're getting like, I don't know, it's like 8 rows and 17 circuits or something, I'm like, all right, I got to figure out what these are.
Yeah.
And that's a great example, Braden. It's really helpful.
Yeah. Thank you. Yeah, no, I always think these ones are a really good one there too, just to be able to visualize this as well. But yeah, like I was saying there too, in terms of circuits, just essentially are going to be the amount of paths of coil that are going to be going through the coil itself. Why they're important, especially when looking at the performance of coil itself, is that as we start to maybe increase the amount of circuits that are on there, so say even like a 19 circuit or 17 circuit coil, adding too many in a lot of cases could have some detriment a little bit on your heat transfer, but more importantly, like that laminar flow range of what we were talking about there earlier might get less predictable in that performance, as that fluid distribution is distributed into so many different fluid paths that it gets below that 0.3 or 0.6 GPM per circuit target. But then also, if we start to decrease those amount of fluid paths, adds a higher amount of fluid pressure drop that is going to be inducing on our system there too. And a good way I'd say to visualize this just as a fluid level, again, is a comparison maybe looking at that maximum amount of GPM that can go through one of these water coils versus the maximum capacity yield and how much additional fluid pressure drop that is going to be adding on our system. This is just looking or evaluating at a single circuit coil. And what we'll actually see when looking at these coils is that the maximum 87% of our possible capacity of that coil is actually dictated at 50% of that fluid flow. So for any of you that are maybe dealing with a situation that you're not quite maybe getting to that capacity targeted, or trying to even add much more fluid flow through this coil and not seeing as much gain through the coil itself, why that's caused is that a lot of that additional gain of what we're seeing on our capacity is for that first few 50%, let's say, of fluid flow that's passing through the coil. So common, I'd say, rule of thumb of what I even see in industry, especially when dealing with circuitry with a coil, is it's around that 2 GPM per circuit mark is where you're starting to get maybe around that 50% maximum GPM of that coil is kind of maybe a tempered mark of what you might set. And that's going to get you around that 80 to 90% amount of capacity from that coil at a reasonable fluid pressure drop that's going to be added on our system there. And the last one here, I'll just touch on here briefly, as it's not going to have as much, I'd say, influence, or this is more steady state in terms of how these coils are manufactured, just from an air moving perspective, is just going to be those hairpins in terms of where they're connected. So we mentioned there earlier, 1/2-inch tubes, more typical, and what's going to be utilized with air moving equipment there, just for allowing for that energy efficiency that's going to be going through those tubes. Tom had mentioned there earlier, well, what about 3/8? Well, commonly we see those at much lower or smaller coils, and what those might be utilized for. And then any of you that asked to have maybe higher amounts of rows of coil within the system, that's where you might start seeing that for some rooftop equipment that would be utilized with 5/8 larger coils there as well. So now that we've evaluated some of the different components or main components that make up a coil itself, let's actually take a quick look here at one of my favorite parts there too, of just looking at the process of putting these coils together. So down in our Progress factory down in Georgia, we have our own manufacturing facilities just strictly for water coils and where these are going to be made. So those hairpins that we talked about, in expanding it to that 1/2-inch diameter there as well. The fin press for being able to set out in terms of those heights or fin density and combining them together. That's some things that you're going to be seeing on screen here there as well. For being able to split in terms of what we're going to be seeing on our header connections for dictating how many of those fluid paths are going to be going through for our circuits. That's what we can see here for that dual head T-drill, just for making that manifold in terms of where our entry point is going to be, as well as our leaving point. And then also that brazing process, just to make it more quicker and effective there as well, having an auto brazier for those components, what they've all been assembled there together.
Yeah, I have a comment and then I have a question for you, Braden. So the comment is, when I first signed up with Price, because everybody was using 180 or 160 degree water temperature, the whole industry bought all their coils from the same couple of vendors. It was like USA Coil or like American Coil or something like that. And now that the constraints of design are getting to be tougher, and of course Price has grown a lot. Now they're making a lot of their own coils, and you can see for a process like this, is it like, hey, we want to start building our own coils, we're just going to order up a coil making machine, or is there more to it than that?
Mm-hmm. Yeah, definitely a lot more for say putting into the manufacturer level and design time that's going into and configuring these coils.
I mean, but do you just buy I assume you just buy like a hairpin bender or
Oh, correct. Yeah. So yeah, just buying some of these different equipment for being able to put these together there.
Right, they're not necessarily price originals. It's more like an
Right.
equipment
More
investment.
equipment thing of what you would see industry standard or up to code for what you would expect for water coils that are going to be made within the industry. For us there too, right now we just focus on reheat and cooling coils that might be paired with our equipment. There are some DX and other manufacturers that you would see there within the industry, but we're just not at that point for manufacturing this equipment. And yeah, here's just a couple additional examples there, just close up of some of my favorite equipment there too, with Frank working the machine there too, just for bending those tube passes that are going to be going through it, and then also expanding as the tubes are going to be inserted through those fins through our tube expander. Also with these two, very commonly enough, and that kind of ties into having everything in-house, is being able to customize or look at different circuitry that you would see more so once we start looking at fan coil and blower coil equipment and customizing the sizes, but then also in terms of a specification level, also testing all these coils before they're going to be shipped out to make sure that they've gone through and have been rated to a certain pressure requirement before they're going to be shipped out too, just to ensure that we're not going to be having any leakage. So very common that we're going to see that need to be tested around 400 psi or above that 390 psi requirement when doing some of the static testing. And with that, in terms of customization and where that also comes into play, we'll kind of briefly go through this there too, because I want to be cognizant of time for this water coil portion that I really wanted to get into the example. So this also does open up the level for different custom solutions that can be paired with this equipment. Commonly what you'd see, just because you're not going to be always operating at design day conditions, so having different valves and components to modulate that fluid flow as it goes through that equipment as well, is also having the option for valve packs or piping packages that can be paired with this equipment. Beneficial both from a quality control perspective, but then also for cutting down on the amount of time, both for installing on site, but then also for trying to sort out the logistics for some of these different components. So commonly what we would see paired with this equipment there too, temperature control valves. Essentially, you can even just visualize this as the damper of the system for modulating the flow of what's going to be going from or through that coil. A balancing flow or balancing valve is what that design day or maximum flow set point of what we might want to set for that specific component. And then some form of blowdown valve or strainer, just when we're wanting to filter unwanted particles that might be trying to pass through our coil, so we'd be able to get out of that just when we're maintaining or doing some maintenance on the coil itself. Also allows for different options, and more common, we'd see this paired with fan and blower coil equipment there too, to ship as a full package for having all these different components for both 2-pipe and 4-pipe configurations there too. And this, similarly as the dunk test, also does go through QA testing just for being able to ensure that there's going to be no leakage points, and then just even having an additional quality check there of nitrogen sniff testing just at each of these joints, just as this package is being shipped, that there's not going to be any quality concerns. And then similarly, whether it be just a water coil or one with one of these valve kits, also having additional crating that's going to be provided with these, just to ensure that these coils are not going to be damaged when they're going to be shipped out to the field there.
Yeah,
Okay,
I've got
Brayden.
a couple of quick questions in here.
Oh, for sure.
One's in the Q&A and one's in the chat. Heidi's got one in the chat about, I've got Jonathan's here. Are most coil circuits intertwined?
Maybe trying to understand in terms of intertwined. I'd say, like, in terms of if we were to go back here, just to hop back to our example, maybe the best one to look at is actually going to be this 9-circuit example there too. In terms of the passes, yes, they're going to be intertwined, let's say, or having the same connections of what's going to be flowing through the coil. This one, as you start to get larger, it starts to get more of a unique pattern of what we might not see. It's not as much of a helical pattern. Reason for that being, too, we want to try to maximize how much space or additional depth that adding these additional rows is going to have on that coil. So it's more typical to have it more, let's say, intertwined. Have we looked at splitting circuits vertically or horizontally? Yes, we have looked at some different configurations. We actually did some studies with the University of Berkeley for evaluating different circuit patterns of going through the coil, whether it be vertical or horizontal, different patterns there as well. There might be even more room for adding or optimizing the overall coil itself. But with that, it's also the trade-off of maybe the additional size that might add to the coil, or maybe not as unique or more unique sizes that might not pair with, say, a terminal or fan coil equipment, because we're more constrained and we look at a little bit of what sizes we actually can play with when we're talking about, like, say, a 12 by 10 inch VAV product. There's only so much space in terms of how much we can intertwine those fluid passes that are going to be going through there. So with that, that's why you might see a little bit more restrictions or in terms of what that overall profile is going to look like on a circuitry perspective.
Then there was a quick question from Heidi. If you could go back to that pre-piping, can you just show where the bleed valve would be on that?
So normally, like each of these will have ports on them in terms of each of these, like on the Union, it would have a bleed point there too. Each of these valves can have one that can be added to it there as well. As a standalone coil, we do have the option to look at adding that there as well, if it's not just going to be built in fitting in the field there.
Great. Am I encouraging too many questions here? How are you doing on time, Braden?
So right now, I'd say we're doing pretty good. I'm loving the engagement, though. I really like this style a little bit more than just reading to a slide and stuff like that. So yeah, keep the questions coming here too. But yeah, we'll keep working through here. Now we're going to actually look at some of the different options that you have available for your utilization, and we'll look at a case study as an example there as well. So first off, let's look at some of the options then for increasing our delta T at a water coil level. A good way to highlight this is taking it back to a terminal level for comparison, but this is applicable to standalone coils as well as coils that might be paired with fan-powered equipment. So on screen here, I've just had this just for example of where this comparison is coming into play. Here's some typical assumptions that we're laying out for these single ducts before we go through of looking at what some of these different options are. So most common sizes of single duct, we're going to be playing around with different water supplies that are going to be entering them, but very typical entering conditions in terms of a velocity profile for our reheat flows, and then also our entering air conditions, and just playing around with 2-row coils here. So the first one being in terms of being able to allow for additional heat transfer that's going to be coming from the coil is going to be high capacity coil options, or increasing that range. So where we'll see this for fan coils is for high performance fan coils, as well as maybe some of those commodity types that you would see from the windowsill of increasing to a 12 or 14 inch, just to allow for a higher level of heat transfer that's going to be coming from the coil itself. From a VAV perspective, bumping from 10 to 12 fins per inch, just to try to achieve a certain leaving air temperature that's going to be coming from that coil as well. But one key consideration for this to take into account if we are bumping up our fins per inch is just going to be the additional amount of air pressure drop that's really going to be adding on our system. But an example of this when evaluating at 140 degree supply water temperature is that we are able to achieve or maximize what that water side delta temperature is going to be, which could be more ideal for condensing boiler systems. But one trade-off when looking at increasing fin density, whether it be for a single duct unit or once we start looking at fan coil equipment or even just standalone coils, is just the reality of additional pressure drop that's really adding on our system there. So one kind of solution, or being able to highlight just for seeing that as you start to play around with fin density of a coil, this does have an influence in terms of how much capacity that it's going to be providing there as well. Another option for there being, when looking at a single duct level, is oversized casings. So oversized casing essentially meaning that you're keeping the same inlet size, but bumping up to the next casing size. This could be an effective solution, especially as you start to see lower and lower water temperatures that are being utilized within systems, because we're able to keep that same inlet size of that product. So whether our minimum ventilation calculations that have been determined, we're able to maintain that. But now we've got a bigger coil that we can play with. Benefit of that bigger coil? Well, we allow for more heat transfer that's going to be occurring at the coil itself. And then from a fluid side, also a larger delta temperature that we're able to provide from this too, with the benefit of a lower air pressure drop. So good, effective solution, especially on the earlier design phases of being able to look at for, say, single duct units, or potentially even for utilizing a bigger coil, as you're now being able to increase that effective heat transfer area that's occurring at the coil itself. So benefits for both, again, for increasing our water side delta that's going to be provided from our coil, decreasing our fluid flow for potentially of how we're going to be sizing our pumps, and then now at a reduction of air pressure drop. Where this is going to be tying in, though, and when we look at a retrofit example, is it always possible to oversize a coil, or how much coil can we oversize before it becomes a concern? But we'll talk about that here in a little bit.
Well, I'm empathetic, because all the folks that are trying to lay out high efficiency projects probably aren't able to have the discussion with the architect. Hey, if we're going to lower our water temperature, we need a lot more vertical space, horizontal space. They just say, we'll make it work in the same amount of space that you did when it was 180 degrees. Like, that's all we've got allowed. And it's like, boy, oh boy, how many more constraints can we be working against?
Exactly. Yeah, it's crazy. It seems like it's always shifting and getting lower and lower. And then now it's just even on the equipment level, getting more and more difficult, and having to come up with different ways to be able to achieve those targets, and when we see them coming within a system. And this is also just highlighting that utilizing oversized casings can be effective for both optimizing reheat and airflow measurement. Just the reason for that being that as you might have lower minimums for your valve size, being able to bump up the casing size but keep that same valve size can be an effective solution when looking at water coil performance that's lower for a VAV. So a typical, I would say, rule of thumb for you on the call there as well, for everyone there too, when dealing with conventional boiler systems, are around 180 for, say, terminal water reheat. That's typically going to be most effective with a one-row coil. Condensing systems or condensing boilers around the 160, 140 mark. That's when we start to look at two-row coils, or maybe these oversized casing or high capacity options. And then as we get to lower into heat pump range of around 120, that's when you start looking at maybe bumping up the amount of rows, or potentially playing around with the circuitry of that coil to be able to handle these lower temperatures, or maybe more custom coil solutions for that there as well. So the last portion here, just to kind of combine, we've made the coil, we know how to calculate it, we know some different parameters that are going to have an influence that performance. So the last kind of ending portion, just to kind of tie all of this stuff that we've learned off, is looking at a retrofit example, specifically for a hospital setting. So on screen here, I've just listed out 5 different sizes of reheat coil that's existing in a hospital system utilizing a conventional boiler. So what we're going to be seeing here is our common targets. So at 180 degree entering water, EAT or entering air of 55. These are currently one-row coils that are within our system. But these current targets of where the system was designed is ideally having a air pressure drop below a 1/4 inch and a fluid pressure drop below 5 feet of head there, and just targeting that water side delta of 160, or what's more going to be effective when looking at a conventional system. Our dilemma, though, and what they're looking at doing for this retrofit is converting it over to a heat pump system. So now what we're seeing with that conversion on a water side is now we're running 120-degree entering water in our system, and kind of begs the question when utilizing this now on a component level, or when we're looking at our water coils, is a coil retrofit also required? And the answer to that being yes. If we were to look at that same schedule and convert and then just instead supply 120-degree entering water temperature to those coils, what we'll see is a drastic drop in terms of not only our leaving air temperature that's coming from that coil from those similar conditions, but the overall capacity. So you even see this jumping down by 1/3 or 1/2 in some instances now of that same 1-row coil, of how much it's really achieving once we start to pass this different fluid flow that's going through our system. So with this, it kind of opens up, based off what we learn, of how might we be able to achieve some different capacity targets, or be able to achieve that. Maybe open it up to the field of what we think we should do next for this system. I guess maybe even to enter in the chat there of what are some things that you think we could do with these existing coils to try to get us to those capacity targets that were previously laid out. If not,
I'll give you one.
Okay.
The laziest one of all of the above, right? Like you're gonna have to how are you saying increased water pressure, replace coils with more rows? Well, it was rows, thin density, and I think based on what I've learned about the Vantage boxes, reduce the number of circuits. Limit the number of circuits.
All good points there. Yeah, I think a really common one, we'll go through some different examples of some questions that people might bring up there too, but appreciate your response there, Tom, and also Heidi there too, is first, is it realistic to make that coil bigger? Well, no, not necessarily, because then that really creates the dilemma for us, both from a footprint perspective, but then now, as we increase that coil, the amount of additional airflow that we're needing to provide to that same coil performance. So as you see here, for those same reheat coils, much more drastic increase, or nearly double the size of the same coil of what would be required to achieve that same performance there. Sorry, a little bit of a tongue twister. The next one, of what Heidi even alluded there too, is reality of we're having to look at potentially increasing the amount of rows of coil that's going to be happening with that. So if we were to still try to achieve that same 20-degree delta of that low water temp that's going to be leaving that coil, and bump these instead up to a 2-row coil, what we're going to see on that same schedule is good. 3 of these coils now are able to achieve those targets. But a few things that we're also going to really notice here too is a little bit higher fluid pressure drop that was initially set up for that schedule. Initially, they were targeting less than 5 feet of water gauge for that. Now we're seeing a little bit above 10 feet for that coil itself. And that's one consideration that we're going to have to take into account. But then also the consideration that this air pressure drop of this coil is starting to get really close to that 1/4 inch that was initially laid out. So if we were to try then for those 2 remaining tags that were not quite there, what we'll see that now these are also able to achieve those capacity targets that were initially laid out, but also now at a higher fluid pressure drop, so just above 10 or around 15. For those existing coils, and then also slightly above for some of them that 1/4 inch water gauge target of air pressure drop from that coil. So Is it possible? Yes. One effective way, especially when looking at retrofits, as Heidi had mentioned there in the chat there too, is actually going to be increasing the rows of coil that they're going to be connected to. But one kind of takeaway or reality of that, if you're dealing with retrofit projects, is that you're going to have to consider increasing the amount of water pressure drop that's going to be happening at that coil, and then also potentially tweaking of what our threshold is going to be for the amount of air pressure drop that's coming from the coil there as well. We can't just bump up the size of coil because it's probably going to be much bigger. That's not going to match the existing footprint or ductwork that's likely within those systems. So a likely scenario that we're really going to see, especially when looking maybe more at like terminal retrofits or fan coil retrofits, as you're going to have some limitations in terms of what circuitry or fin density adjustments that you really can make. A lot of the cases, this is going to be an adjustment of rows, but again, some considerations just for how much adjustments of our targets are going to be for fluid pressure drop as well as for air pressure drop. And with that, I would say that's part one of our presentation about water coils. I hope all of you learned a little bit more of kind of having that deep dive of both on a manufacturer level, what some of those restrictions are going to be, but then also how some of these different performance parameters or geometries can have an influence on the coil. I guess I'll briefly just open it up here just before Tom gets back here as well. Just any questions that people might have, or maybe even some projects that they currently have on the go for when dealing with water coils specifically.
Unless you need a couple minutes, and I can entertain the crowd with a video or something.
No, that's okay there, Tom. I had a couple sips of coffee here, and we're ready to go for part two. So
let's roll.
Let's roll. So yeah, we learned about coils. Now we're going to be talking about fan coils. Very effective solution, especially when pairing with these water coils for addressing heating or cooling needs for a space. I guess just as maybe just a understanding for myself, how many of you in the chat there deal with fan and blower coils on a day-to-day basis? Is that something typically that you're seeing within your designs or work with, or for some of you contractors in the call here too, have been installing with or working with this equipment? Feel free to just even drop in the chat there. If not, no one's ever seen it before, even better. More room for growing there. Well, Kevin, thanks for your response there too. I think it's even can be dependent on area or even depending on firm preference and stuff there as well.
You know, it's interesting because way back when we hired this sort of energy expert, Stan Muma, to come to a CRC, and he said his most efficient design buildings were DOAS paired with fan coils. And I don't see that design very often here. I mean, I do see DOAS with BRF, I see DOAS with chill beams.
Mm-hmm.
Not a lot of DOAS with fan coils. I'm not exactly sure why, because the fan coil is just such a simple device.
Mm-hmm.
Maybe it's the distributed fan. Oh, of course, DOAS and heat pumps too.
Mm-hmm.
But it seems like a pretty simple solution. So maybe we'll change some minds here.
For sure. Yeah, and I've seen some responses here too. Some it's a part of their day-to-day. Some see it come up occasionally there too. But don't want to assume anyone's background knowledge, especially if this is the first time ever seeing this equipment or learning a little bit more about it. But essentially, with a fan, simple level, you got a fan and a coil, where essentially it's going to be pushing or drawing air through this coil before it's going to be delivered to the space. With this, a lot of the times it's going to be provided with a cooling coil. More typically, I'd say in terms of attachment rate, 95% of the time, heating coil as well there too for supplemental heat. But essentially that's what's going to be providing some cooling or heating to that occupied zone when it's going to be paired with this equipment. The other form of equipment of what we might see is I like to visualize as just the bigger brother of a fan coil is going to be a blower coil unit there itself. Commonly, I'd say in terms of difference between blower coil and fan coils, it also has a motor. It does also have a coil, but a lot of the times these are configured into draw-through configuration. So you have air that's being drawn in through a coil from a fan before it's delivered to the space for a blower coil, and vice versa for a fan coil pushing air across the coil. But also key characteristics or difference between the two of these there too is the amount of static pressure that these fans are really working against there as well. So with blower coils handling higher tonnage and higher airflows of what we're going to be seeing within the system, and more commonly than not, especially when looking at fan coils specifically, these ones dealing with more lower static applications. So I've seen some of you mention for single zone applications, so up to negligible amount to a 1/4 inch of static in terms of what it would really be handling. Whereas once we start to get into blower coil territory, that's when you start to get into that 1 inch to upwards of 4 inches of total static of what that blower coil is really trying to compensate there for there as well. All these ones there too, and you'll see with some of the renderings as well, having some form of drain pan for that condensate management system, just because the likelihood that there is going to be some condensation that's happening at the coil there itself. So we mentioned that all of these come with a fan. Well, what type of fans are these commonly provided with? For a lot of those retrofit systems or ones that you would see within the past, a lot of these were paired with PSC motors or permanent split capacitor motors in the past of what they'd be run with. But what we're starting to see, not only when we're talking about water coils of an industry chain of higher temperatures for our chillers or lower temperatures for our boilers, but also from an energy perspective, is a lot of fan coil manufacturers are even shifting to utilizing EC motors with this equipment there as well. Both from an energy savings perspective, but then also for sequencing side of things, of any of you that have helped out with startup with these, for being able to have fan status and also provide some level of external modulation through our building management system of how much airflow is going to be achieved from that motor itself. In terms of fans that are commonly paired with these products, the most common one that you're going to see are these forward curve fans. Pretty effective solution, I would say, for low static applications or operations. And what I mean for that when talking about this equipment, normally you're going to see these up to 2 inches of static or below that, especially when dealing with fan coil equipment. And then once we start to get into the more specialized zone, let's say, or starting to get into 4 inches of static or even higher than that for feeding into systems, that's when you might start to utilize plumbing fans. Reason for that being, do have a higher cost platform that's going to be associated to them, but it expands that overall pressure capabilities of how much that it can handle. So how large the space that it really can serve, and then also the amount of coils that we really can add to this product, which also, what we'll learn here in a little bit, can be beneficial from a sound level perspective there too. We mentioned cooling coils, and that's even like a key parameter that really distinguishes the difference between terminals to fan coil and blower coil equipment. The reason for that being, and how it's different than these VAV systems, is that it's also handling latent cooling. So those wet bulb temperatures or reduction of humidity or condensation that's going to be happening in our system. You're now having entering temperatures through these cooling coils that are below that dew point. So when we mentioned that all these products come with a drain pan, reason for that being, there is going to be some condensation that's going to be happening in that coil. That's just a means of being able to mitigate that when we're trying to adjust to some of the humidity control that's going to be going through it there too. And with these as well, similarly, also being able to handle those sensible cooling conditions for the given space, we can also make it, and why it can be an effective strategy, especially when we start to look at DOAS systems and pairing them with these fan coil and blower coil equipment there too. And at the coil level there too, and how this ties into part one of our presentation there as well, for being able to lay out in terms of rows and circuitry of what's selectable for a fan coil as well as a blower coil. Rows, again, when we're looking at there, allows for a higher level amount of latent or sensible capacity that's going to be provided from the coil, just at an additional amount of pressure drop that's going to be inducing. I know we mentioned this earlier there in the presentation, but for fan and blower coils, this typical row mark is going to be up to 8 rows as a kind of a maximum of what we would see in terms of a cooling coil or heating coil that can be paired with this product. And then circuitry, the amount of fluid paths that are going to be going through the coil itself. And the fact that we're dealing with bigger coils, I think Jonathan mentioned that earlier, just a little bit more customizability in terms of what circuitry that we can play with when looking at fan and blower coils. Another key consideration when looking at fan and blower coils, what we'll see in some territories, I don't know if it's, I don't believe it's as applicable to your territory there, but also 4-pipe configurations for fan and blower coils, where essentially it's going to have an individual coil for heating and another individual coil for cooling. But based off of where that heating coil is positioned and cooling coil is positioned, is going to dictate of what terminology or verbiage is used for that configuration. So for example, on screen here, a preheat condition is having the heating coil before the cooling coil. Beneficial for this is for handling any outdoor air that might be going through this product. So effective strategy when dealing with lower entering air temperatures. And for reheat configurations, this can be very beneficial if you're running both of these coils when looking at dehumidification within the product there as well. So what we see more commonly than not, 80% of what we see when for firms that deal with 4-pipe applications are configuring them for a reheat configuration. We mentioned there earlier, and there's a comment of, well, maybe how much space do I need for a water coil when maybe looking at, or maybe an extension when looking at equipment, such as a fan coil or a single duct. Well, with fan coil specifically, they also have its own rating program through AHRI for the fan coil unit as a performance as a whole. So it's actually testing that water coil with the fan coil. So it's taking into account any concerns that you might see, especially for close coupling or having that fan position close to the coil itself. And from an acoustics perspective, or how much noise is going to be emitted from this product, also some testing for both ducted, as per AHRI 260, and unducted applications, or AHRI 350 for these products, just because what we'll see here in a little bit, it's common to configure these in both of these applications there. And the last component, because all of these products are also being provided with filters, is consideration of what filters are being added to these products. With fan and blower coils, what we're seeing is a shift to thicker and thicker filters that are going to be paired with these products. Benefit from that is not only from a filtration perspective, but by increasing that overall surface area of that filter, what that actually does for us is a decrease on the amount of resistance or air pressure drop that filter is adding to that coil, or sorry, that fan coil, or that blower coil here. So for example, we're seeing a step to a 2-inch or 4-inch filter, almost halving the amount of air pressure drop that's happening at that filter, as it's going to be having air passing through it for its first resistance. And where that really ties into, especially when looking at, say, fan coils as well as blower coils, when comparing and adding thicker filters or thicker MERV 13 filters on these products themselves, benefit from the reduction of air pressure drop. You're going to see it's almost halving the amount of air pressure drop that filter is really adding, that fan's trying to compensate for both these fan and blower coils, which is also beneficial from an energy savings perspective. So how hard that fan or how much consumption is happening from a power perspective from that product. And then also by having a little bit less turn down or how hard that fan's trying to work, less sound that might even be added from adding these thicker filters on these products there too. So that's kind of overview of fan coils and blower coils in general. Again, a fan, a filter, and a coil that's pushing or drawing air through it, deliver the space. And now let's start to look at some of the different systems that we see there as well. And when talking about a system approach, and I think this is going to be really good, especially before we talk about a case study here or example here in a little bit, is consideration of system pressures or how they apply when talking about fan and blower coils. And with this equipment, a lot of the times this is taken into account as external static pressure in terms of the total resistance that that fan is trying to compensate for. And how that really ties in is, well, how much additional static is our downstream conditions adding to it, that whether it be our duct lengths, bends in this ductwork, or GRD downstream from the product itself. Then also for ducted applications, how much return static are we seeing there as well, whether it be connected to other zones or other spaces, or how long that trunk line is going to be that fan is trying to draw air through there too. In terms of different approaches of what we'd see in terms of piping configurations here, one configuration that we'd see, and this is an example of just a reheat configuration for 4-pipe, essentially having heating and cooling supplies that are being run through that same equipment, depending of time of year of what those building needs are going to be. But one very common approach, instead of having additional valves within the system, just for having this form of changeover for these different equipment of what you'd see even for these trench heaters on screen here, or for these window seal commodity vertical units, is also having 2-pipe changeover systems. So instead, just having one individual coil that's both operating depending of your summer mode as well as your heating mode needs for wintertime there as things start to get a little bit there cooler. So some advantages I would say for 4-pipe systems is what we're going to be seeing is simultaneous heating and cooling that can be beneficial for some what we would see for some dehumidification within the space and allowing for that fast changeover. But a lot of the times, and where we might not see these used, is just the fact that it does come at a more or higher cost. And then in terms of adoption, it can get more complex in terms of an installation perspective. In terms of 2-pipe systems, beneficial for these, smaller footprint of what would actually be required for installing these. And what we would see there as well is just lower initial cost within systems. And I think when we chatted, I want to say last week there, Tom, you said in your territory, you see for yourself more 2-pipe systems that are utilized within building designs?
Never.
Never for
Almost
2-pipe, or vice versa, it's the 4-pipe configurations? Sorry, I got the mixed up.
Almost always 4-pipe, yeah.
4-pipe, yeah. So, yeah, this is pretty common, I would say, and we're starting to see a lot more, especially when looking at fan coil equipment, more common to provide with 4-pipe systems in comparison to 2-pipe.
Yeah, there's a couple of questions, comments in the chat. Heidi was asking about fan coils serving the same space as the VAV, which I mean, you can make a fan coil system behave like a VAV.
Yep. So even tying in there,
but not necessarily simultaneous. Oh,
right.
You're right here. Look at you.
Yeah. So I think this almost ties into maybe your question there too, Heidi, of maybe the difference of parallel and series ventilation systems, where with parallel ventilation systems, you might just have a fan coil that's addressing more of your sensible capacity requirements for the space, and instead using a VAV for tempering how much ventilation is instead going to be provided within those systems. But then also what we'd see too is options with blower coils for series ventilation systems. And what you'll notice here as well is that you have a blower coil that's addressing both your capacity needs for the space. But what we'll notice on here too is this valve or intake or pressure intake valve on here that's almost taking on some of the responsibilities of what we'd see for VAV for throttling how much fresh air is going to be provided to that occupied zone there instead.
Yep. And then Dan Burr's got a good question, which I often wonder about too. So you've got a MERV 13 2-inch filter, and that 0.2 or 0.21 inches that you had, that is a mid condition, a dry, a clean condition, a dirty condition?
That's going to be dry first load condition or like first initial resistance.
Clean.
That's taken into account. Clean filter for that calculation there, Daniel.
So Dan's got to come up with the external static, which should include some filter loading, which would be another ballpark question mark.
Depending of there, you could even see another like 2.2 inches of what might be added to it, of what you might see for filter. I mean, it depends on type, but that could be the additional amount that you might see with that there as well.
You know what? One suggestion here is that filter loading is almost never in the catalog, and it probably should be.
Yeah.
Because it's pretty common questions like, well, it depends on what filter you're using. Well, let's use the one that we ship with. Yeah. Do we ship filters with, or are they?
Yeah. So they're going to be shipped with the product there too. I think it's almost even a tie-in of, depending of what vendor we're getting, like we don't manufacture our own filters, so who it's provided to, you might see some variance of what they might list as their first or final resistance. So updating or make sure we have the right collateral. But a lot of the testing in terms of static is going to even be built into those calculators for that tested equipment of what we would see. But here's just an example there too, there Heidi and Co. of just a series ventilation system where essentially now you have a blower coil that's serving a long line of diffusers by the perimeter, but then also bringing in your ventilation through that fresh air intake, also paired with this product as well. Benefit of that being for some of the ventilation integration is it's cutting down on some of the additional cost that would be required for adding a additional single duct within this system. So additional duct work that would need to be considered there too. Separate outlet conditions that you might have to lay out as well, a form of controller that we're pairing, and just making sure that those mesh well with the existing equipment within this system. So one consideration, especially when dealing with fan and blower coils, is instead adding that intake or fresh air intake onto the unit itself to be able to cut down on the amount or additional cost that would be required for trying to add an individual VAV to our system there. And that's becoming, I would say, more and more popularized. That's a big word for me for these systems there too.
Yeah, and going back a slide, Braden, so that, or actually one more. So that could be a dry coil installation or a wet coil installation.
Correct.
So you could conceivably, if your DOAS unit is taking care of all the latent, you would have basically not maintenance free because you'd still have a filter and a blower, but at least as far as the condensate and cleaning goes, that all goes away, and you'd have a dry coil, which is pretty nice.
Yeah. And then when looking at even this example being an exposed ceiling application, another consideration that we always have to take into account when talking about fan and blower coils is also the reality of the amount of noise that's going to be emitted from that product. Key driver being just the amount of noise that's being generated from that fan within this equipment, or in the cases of having those fresh air valves from that damper there too. But typically the main driver being that fan. So in terms of different sound sources of what you would see there too, a little bit different than a terminal unit, as you're also having inlet sound on the intake side. Essentially, if we were to look at this, discharge noise being how much noise is emitted from that fan or downstream of the product itself, radiated, the amount of noise that's being transmitted from the casing to. And then now with this equipment as well, as it's typically connected to a return or ducted or even an unducted applications, how much noise is then being generated or breaking out from the inlet side. So different ways to try to design around, I would say, fan coils and blower coils for this equipment is selecting it around that 60 to 80% of its nominal flow range for a fan coil or a blower coil. The reason for that being is that that's going to save a high level amount of noise that's really going to be emitted from the product than trying to run it at full maximum of what used to be more typical of what you would see for a PSC motor, especially when trying to yield as much energy savings as what you could get from that motor itself. But commonly, what we recommend for these is actually going to be selecting around 70% of its flow just to yield less or more of a peace of mind in terms of what performance is going to be coming from it. And I see a question from Jonathan. Does price the selection software calculate noise data at operating conditions? Yes, it does calculate that for both fan and blower coils. And this would be broken out just depending on what airflows and pressures that you're going to be listing for the unit there itself. Also consideration there as well, depending of where this is going to be positioned. So if we're dealing with exposed ceiling or closed ceiling applications, that's when we also could consider or look at different attenuation options for these units, whether it be silencers or attenuators to try to minimize the amount of breakout noise that's going to be coming from that unit or from that fan. But yeah, I guess, and feel free, everyone, keep throwing stuff in the chat there as well. But now that we have an understanding of
Braden, there was a quick question about does price include sound levels in their selection software? And the answer is yes, and it comes in both the 2nd through the 7th octave bands and both discharge and radiated sound. I think there's a return sound, and then also an NC, but it's really important in the NC values of a fan coil to know what the test setup is.
Right. Yeah, because with NC in terms of how it might be perceived, or like it kind of ties into when talking about NC of how it might be perceived, but a lot of times with those calculations are done based off a certain standard, which might always have those conditions that you would see within a certain space, whether it be its size or different attenuation features or etc. But now that we know about fan coils and blower coils, let's start looking at some of the common ones that we would see within industry. Some of you, this might be familiar, some these might be brand new, but likely you have seen them before, even if you don't commonly work with them. These are these concealed horizontal and fan coil units, essentially a commodity style unit where they're dealing with those single zone applications. So commonly where you might even see this, if you're traveling or on the road within a hotel room, very common to see one of these maybe installed by the window wall or right above the bulkhead, also in smaller office spaces where you might see. But essentially with these products, lower static or less than 1/4 inch of what they might be dealing with, as well as at lower airflows. So up to around 1200 CFM is where they're going to be the most effective. And one thing you'll notice even for this horizontal style, as a lot of times ceiling is a premium, is that a lot of times it's more of a restriction on what its maximum height is going to be. So they start to build out what its overall width is. Reason for that being, and we learned during our water coil class, is that by also increasing its width, we're just maximizing and adding a bigger coil face area for that heat transfer and lower pressure drop that's going to be happening on those fans that's paired with this equipment. But with these there too, I also have exposed versions. So instead of having to build around this equipment before it's going to be, or after it's installed in the space, also versions to just have these casings or cabinets paired with the product as well. just to and be able to be installed that way. So maybe a little bit higher of an initial cost, but in terms of install time, that's where a lot of the time savings is going to be there too. And again, very common of what we'd see for a hotel setting.
Hey, Braden, if someone has a design that's outside the parameters of these various models, like, okay, I see, Bryce, that you have a 7.5-inch deep cabinet. I don't have 7.5 inches. I have. Is it just too bad, or do you guys ever look at those too?
We do look at those there too. So if any of you are running into instances where, I mean, say if you're ever running to ceiling space is a premium. So as you see these projects come up and maybe you're running into issues in terms of, let's say, sizing of equipment, trying to fit it within the space, we can look at different options of potentially playing around with overall sizes, or what we'll see with these there too, where those enclosures or shrouds are going to be positioned on the product as well, to try to save in those access points or when you're setting them up within your BIMs or Revit files there as well. So there is some customizability based off of if you're running into some footprint struggles. So feel free to bring those up whenever they come up with Airflow and our team here there too.
Okay.
Another version of what you might see here too is going to be recessed models. Essentially, you can visualize a lot of the times it might even be paired with even beam systems, but essentially now you have a fan that's going to be drawing air through the coil itself, but installed in a 2x4 ceiling grid or 2x2 ceiling grid for essentially also allowing in these smaller spaces for having a lower installation cost, as you're not having to worry about any additional ductwork, and you have the existing grid system for there too, but being an effective solution for adding some additional cooling or heating for these spaces and additional air changes there as well. And this kind of shifts into some kind of the bridge point between fan coils and blower coils. And this is high performance fan coils. And what you'll see here too, that bottom unit almost looks like a transformer, very long. Likely there might not be cases where you might have, like we've been talking about, struggles within ceiling spaces, but this is just an example of a very customized solution that has inlet and discharge silencers married with the fan coil itself, just for very noise sensitive applications. Normally too, it would just be the coil and this casing itself, but just shows some of the capabilities, especially for very sensitive spaces for where it's trying to handle this. And one interesting perspective there too for these silencers is that they've been specifically designed and tuned, I would say, for this product, where it's actually matching the flow positioning of where that flow is leaving that fan or that coil as it's going through the silencer itself, just to maximize the amount of attenuation that these components are really going to be adding on our system. Another one too, which is almost the big brother of some of those commodity horizontal units too, is what you'll notice here. Instead of adjusting the width, we're adjusting the height. Similar benefit of air pressure drop and adding a higher amount of airflow that we can be provided from these units. And these ones are kind of that bridge point once we start to get around that 1 inch, 0.5 to 1 inch of static that this fan's trying to compensate for, where it might make sense, not quite make sense for that first initial cost of a blower coil, but not enough capabilities of a concealed or commodity type for being able to handle those conditions. So yeah, with these ones, larger spaces of where we might see these, whether it be educational rooms, a cafeteria, and larger commercial zones within, or even within bigger spaces there too.
Historically, with other suppliers, that high performance fan coil has always given us sound fits, because you've got the same blower, maybe you have an EC motor, maybe you don't, but you've got that 5-pound, 10-pound analogy that we often use, and it's usually in a tight space, and they can be loud. So it's something that, if the engineers trying to be conservative and put a 1/4 inch of static on it, and then you've got a MERV filter and you've got 8 rows of cooling and heating.
Yeah.
Oh boy, it's tough. It's tough.
Yeah.
And I'm sure if we put it in the chat right now, we'd fill up the chat with who's had a sound problem with a fan coil before.
Yeah.
So don't fill it in yet.
Yeah.
At least yet.
Chapter 1, struggles. Yeah. And shifting into the last components of what we'd see here there too, with just blower coil units. So these ones also have versions of horizontal as well as vertical configurations. With these ones though, now we're getting up to 15 tons, let's say, of cooling, or 6,000 CFM, much greater amount of static that we're being able to handle within these systems. Commonly, let's say, installed in a maintenance closet or a bit further from the space, just for some of those consideration of noise of what for that product, because it's almost acting like a mini air handler for this system as it's starting to see these points. But yeah, and what you'll notice here as well, vertical version, but even for this blower coil on screen here too, we're seeing one of these plenum fans installed in them as an option as well. What that's really allowing for us to do, and we learned a little bit earlier, even more pressure that fan can compensate for. So up to 4 or 5 inches of total static from what that fan can compensate for, and higher airflows, which is beneficial for really big systems, or what we'll see here too, maybe even if any of you do hospital work, for where there's requirements for final and pre-filters in systems, or MERV 14 filters for the ASHRAE 170, I want to say, for those spaces. Beneficial for that too, just because now with a bigger or more effective fan, being able to compensate for these bigger HEPA filters that are being paired with these products there too. So kind of even more of a kind of applied a solution that could be paired or married with those designs too.
Yeah, what you can't really do with that fan coil is take 25% outside air and mix it together with the return. You can't do that. But if you're going back to that, DOAS fan coil unit, you don't really need a DOAS. Like if you have just a heat exchanger to pre-treat your outside air, so your pre-treater is going to be like, you're going to be 45 degrees in the wintertime, and you'll be down to 80 in the summertime. That fan coil can handle it. So dump the DOAS. You can just put a wheel system with freeze protection if you need it, and then go right to these fan coils, and you've got yourself a system.
Exactly. Really good points. And then briefly go through this, just because we already mentioned some of the different applications, but what you would see there too. Here's just some examples of some applications we've seen them utilized for. It's not to say that you have to use them for one of these applications, or fan coils or blower coils can be used for a different application there as well. But just some examples that, hey, if you see any of these work come up, whether it be life science, education, universities, dorm rooms, stadiums, fan coils, blower coils can be effective solutions for a lot of these different projects that you might see. The last portion here too, kind of maybe going through an example of how to size a fan coil. So now that we look at the design side of things, what does this typical layout look like when laying out a fan coil for a system? We'll even look at a case study for this. And when looking at fan coils, commonly, it's dependent on climate zone there too, but it's going to tie down to sizing them based off of your sensible capacity for a system. I would say most of the US population's in warm or hotter climates, but not to say it can't be used in colder climates there as well. But more often than not, this is going to be based off of trying to size based off of a sensible cooling load for a system. And how do we really determine that? Well, there is so many different variables, I would say, that can be taken into account when trying to look at what's driving sensible loads within their system, whether it be environmental, infiltration, internal gains, how many occupants are within the space. You'll see those people in this office having a meeting right now, how much sensible needs or offset is going to be required from them. Lots of different formulas or calculations that would really need to be taken into account for this. But more common than not, This is going to be done from different load calculators for a system, just for being able to determine that. Effective, just because they're using the most up-to-date codes for trying to calculate for some of these different variances of what you might be able to see, just for being able to determine that performance. And since we also mentioned all these come with a fan, how do we really size these fans for a given system? Well, with these, we're typically, like I mentioned there earlier, going for design day points, so around 50 or more ideally even around 70-75% of that fan curve. The reason for that being, we mentioned one, being acoustical perspective, also allows us some variability in terms of turn down, or if we ever had to increase what our airflow is going to be required from that product, let's say for potential future proofing a design, or even for morning startup or night setback applications for being able to turn this product off or turn it off in terms of how much ventilation it might be providing to the space. But then also what we would see for a restriction for maximum airflow, now that we're always dealing with latent coils that are being paired for these products, is we're ideally selecting these within a velocity range of around 400 feet per minute. And the reason for that being kind of the sweet spot of where we're not wanting to have any condensate carryover that might be happening specifically from that coil as it's passing through our system. So if we were to look at determining that supply air temperature then that would be required for a given system based off of that air side equation that we learned about there earlier in part 1, what we'd be able to determine based off of this is a specific CFM that would be required for determining what that sensible cooling coil load would be based off of a certain capacitance for a space. So let's say 8.5 MBH here for that system. But then what we would even do when determining a certain sensible load is selecting it and making sure that it's going to be having the wiggle room of being 75% of its maximum capacity. So even applying it to our required sensible load mark, just to make sure that we have that buffer range of being able to achieve what that unit's potential maximum would be there as well. So now we're going to lead in here too, just when considering kind of this case study of a large high density Contractors room. Here's kind of the 6 main considerations that we really need to take into account when looking at selecting a fan coil or a blower coil. Capacity being one of the marks there, and going to be probably our main driver for trying to achieve what our targets are going to be for the space. Making sure that we have enough static or wiggle room for that fan to be able to compensate for as we're upping the amount of coils that are being paired with it, or even adjusting how much ductwork that this product is going to be serving. In space limitations of what we would see for this product there too, in terms of height or overall size of this equipment, if we're all of a sudden potentially trying to bump up to the next unit size to achieve that same capacity. Noise levels, we already mentioned there too, of selecting a certain point within the curve just to make sure that we don't have any unwanted noise that's coming from it. Filtration, different options there too, and hanging accessories. And then finally, also a key consideration, cost. That kind of does that cost analysis. And sorry, I think you're muted there for a second there, Tom.
Oh no, that damn cost always gets in the way of everything.
Yeah, the cost is, yeah. Cost being kind of one of the main drivers there too. But that kind of gives us a good framework, especially as we start to look into this case study here of just keeping all those variables in mind. So here's the example in terms of some of our assumptions that we're going to be using for this office space within this given setting. Essentially, we have a footprint of 800 square feet, certain amount of people that are going to be within this space. So being able to address what our ventilation requirements are going to be based off of a certain square footage, as well as ventilation requirements based off of the amount of occupants. I know there's some other ventilation considerations to take into account, but this is just to simplify our example here today, just for being able to highlight this. We've just pulled what some potential acoustic considerations we would need for an office space setting there as well. And then just some certain loads that we've determined that are required for both our cooling load for this given space as well as for our heating load. And where we'd really even start up and kind of looking at as well is even some of the different system components that we'd need to consider when running through or toggling some of our performance. So with this, having a chiller running around 45 or 44 inches of chilled water supply going through our system, a geothermal heat pump within the system. So we're starting to work with that 120 entering water that can be paired nicely when looking at fan and blower coils, just as we have a bigger coil, and then some different set points as well. And this one's even a DOS example of what you would see there too, Tom, just for this ventilation system for being able to provide with this product. So with all those assumptions in play for both the space itself, what we're targeting, and then also what our system looks like, one of our first steps here first is going to be determining what our ventilation requirements, our ventilation performance is going to be for this conditioned space. So both determining both our latent as well as our sensible loads based off of our outdoor air ventilation of 310 CFM based off of those number of occupants that we would see within that space and that 800 square foot space there as well. And don't worry, I'll be able to send this slide to everyone there too, just so everyone can kind of run through this example on their end there too, if you ever want to use this as kind of a reference point. But with that, in determining what our required cooling and heating requirements would be, this is going to be based off of then using that sensible load that we've calculated, both from ventilation as well as from some of the other things within that space, to determine what our cooling and required cooling and heating airflows are going to be from this product to achieve those targets there too. And I'm noticing now here too, but this is slightly cut off in terms of the entering conditions there too, but this being around that 80-85 mark for our heating side, and then also from our cooling side, that 55 entering for that system there as well. So now what we're seeing as it's a higher airflow is that our cooling flow is actually driving what our required fan size might be for this equipment or for this box. What we learned just to try to optimize our power consumption as well as our acoustics for this box is that we're trying to size this fan based off of 75% of its fan curve. So we're actually going to divide our determined cooling load based off of our sensible ventilation requirements by 3/4 of an inch, and finding that we now have an airflow requirement of around 1275 CFM for that specific box, just to make it more in an ideal range. And what that also drives us to take a look at there too, and we mentioned it, is some other pressure drop requirements for our system. So how much additional filter pressure drop might we need to consider for our system, both even in this one, also taking into account maybe a dirty filter for future proofing for around 1/2 inch or 1/4 inch for a MERV 13 filter, and then also some of those different external pressure drop requirements that we might see there as well, based off of the overall amount of length of duct that's being connected to this product, the amount of diffusers that you might see, if it's connected to return grills. Here's some just example requirements based off of what you might see, and these are typical ranges I also see based off of what your overall duct layout might be, or system layout might be for a system, in terms of some different values that we can really utilize for our external static pressure. But again, taking that into account based off of what our layout conditions are going to look like, and then the amount of filter pressure drop that needs to be considered for that there too. And when we're talking about pressure drop, we also need to take into account and can't forget about our part one there too, about water coils, as they're also having some form of pressure drop that is adding onto our system as well. So when selecting around that 75% nominal range for these units, we're starting to see around quarter-inch to half-inch of pressure for blower coils at that nominal range. And this is just average, just for any of you that might be trying to calculate this, or just for a reference point, or fan coils around 0.3 inches. And with that, we can add all these together based off of our duct configuration, and we're just assuming our second example, or second configuration for discharge duct and diffusers here, filtration, and as well as the coil pressure drop, for a total pressure of 1.1 inches of external static that we need to take into account. So right off the bat, this really tells us that we're now within kind of more that performance window of maybe a more high performance fan coil or a blower coil, and kind of eliminating the potential of more of a commodity style type, as we're starting to have a much higher amount of pressure that we're trying to compensate for within this system.
Just to be clear, Braden, when you're showing the 0.4 on the coils, that's considered internal. You're looking at the total. You're looking at the total static for the system on just the thing.
Exactly. Correct.
Okay.
Mm-hmm. And with that, it kind of alluded there to eliminating the commodity style. If we're to look at high capacity fan coils or blower coils, we can then plot these out on their fan curves, and this static pressure mark essentially laying out the external static pressure for that system. But being able to, I'm noticing this would be a little bit higher for these fan coils on here as well, reflecting around 75% of that curve, for being able to understand where its reference point is going to be for our actual required cooling condition, but then also plotting out our maximum just to make sure that this is even achievable for that fan coil or blower coil that we're plotting it on there too. So splitting out, that's with internal with that total static, and then 0.7 inches for our external static, just for our duct conditions as well as our filters for those systems. So we can see that it is within the performance windows for these high capacity fan coils as well as these blower coils. But then it really then ties into, well, how does this perform with our part one there of water coil performance? So if we were to look at then plotting out both our cooling performance and heating performance for these blower coils and fan coils at both different rows or sizes from them, at those same airflows for both our cooling as well as our heating side, we can start to evaluate to see, hey, first, are we achieving our capacity targets for this system? Is this within a delta temperature that's ideal for a heat pump system, let's say for your heating performance, or for our chiller for our cooling performance? And making sure that when we're adjusting these rows, as we know in the background, there's also some parameters that are happening with our circuits and other construction of how depth it is, that it's not having an influence on other concerns, such as our fluid pressure drop, as well as our air pressure drop that's coming from the coil itself. And with that, what we're even seeing with this when plotting it out is that across the board, at least for this case, because we are dealing with lower temperatures, a bit bigger of a coil is being more beneficial for trying to achieve those waterside delta targets for the MBHs that are currently listed. Because we learned there too that bumping up that initial row of coil is going to maximize the first potential gain of the amount of capacity that we're really going to be yielding from that coil there as well. So now that we have the coil performance, we've plotted it out with airflow as well. It kind of allows for the direct comparison of all those different variables that we really talked about, being cost, overall footprint of the product, and then also the amount of sound that might be emitted from that product there too. So trying to make sure that it's within the same the performance window that we require. And maybe even opening up to the floor of what model would any of you choose with what you see on screen here.
Well, I know how it'd go mostly. It would mostly go the least expensive one.
Yeah.
And then we deal with the problems later, but
Yeah.
I don't know. This is a what I'll share and what we don't have time for today is when you use Price's software to pick fan coils, you don't have to go through the selection of blower coil 12, high capacity fan coil 12, and high, like it's all put. You can see all the data at the same time, which is really nice. So this side by side that Braden put together is sort of at your not exactly at your fingertips like this, but it's pretty close. So you can see multiple fan coils at the same time with sound data, with the pressure drop, with the coil performance, with the number of circuits, with the number of rows, et cetera, et cetera. So there's a lot there, as you know, because we did do a fairly deep dive into fan coils and coils.
Yeah. And not necessarily any right or wrong answer, but Tom alluded to it there too. Likely it would be the second option, or HCFC12, lower cost, but relatively being able to be within ideal acoustics range at a little bit smaller of a footprint for achieving the same results. But again, it just allows you to show that there are different ways of going around or potential solutions, whether it be a blower coil or fan coil, for laying out these systems.
I think fan coils are inherently problematic for sound because there's usually no flex on them.
Yeah.
And flex solves a lot of problems acoustically.
Yeah.
Well, if we were in the live studio audience at Airflow, now would be about the time that we would be giving Braden a nice hand for his efforts in putting together this fan coil class. And I would like to thank all of you for joining us today. We will hang out for a few minutes to answer any additional questions. Feel free to hang out. And if not, feel free to sign off. And thanks so much for attending. We are going to cancel our dust collector class. There will be an email out about that, and I'm looking to replace that with something with Dun and Bush. But more on that, just follow along with the blog. All right. Thanks, everybody.
Perfect. Thanks, everyone.